So when we talk about the limit of a sequence, we often think about the limit of a function as that function goes to infinity, and there's a good reason for that. Let's just take a look at, I'll draw a sequence, and it doesn't really matter where the sequence starts being indexed, but let's just suppose this is 1, 2, 3, 4, 5, 6, 7, 8. Okay, and let's just suppose that it looks like it's going to limit maybe to some number around here as we go on. And let's suppose we have a function that is compatible with it. And what do I mean by compatible? I mean that the function passes through all those points. In fact, this function doesn't even have to be continuous. It just has to match up with all these points. Differentiability is not important either. Just anything that connects the dots. Okay, so we've got this function. In green, I've got f of x, and I drew in blue a sequence a sub n. All right, and notice that since the function always passes through the points given by the sequence, we have this nice equality that a sub n equals the function when you plug in the number n. So that would be f of n. Okay, so basically this function behaves, it extends the sequence to all the real numbers. All right, and often we'll just think of this as we have a formula for a sub n. We can just think of that as a function by replacing the n's with x's. And what I want to notice here is that, look, if this function f is going to limit out to infinity, and we'd write that as the limit as x goes to infinity of the function, and it looks like here it's limiting to this value L. And this is a theorem that if you can find the limit of a function as x goes to infinity and it equals the L, that immediately means, as long as that function is compatible with the sequence that we're talking about, they're equal to each other on the integers, then the limit as n goes to infinity of the sequence is also L. Right here. And what does this mean for us? At the end of the day, what this says is that these problems where you have to take the limit of a sequence, often we could just think of, well, let's just make a function and we could just deal with the limit of a function. We did all this, we did these sorts of limits in Calculus 1. And so what that means is in order to solve our Cal 2 sequence limits, we'll just convert them into functions and take the limit of a function as x goes to infinity. All right, let's put that to action. Here's an example that says use factoring to compute the limit as n goes to infinity of that fraction. And so what I will do is I'll just say, well, heck, that's the same thing as the best function to pick, as I said earlier, is just replace all of your n's with x's. All I want to know is what's the limit of f plus x over x cubed plus 1. This is the exact same thing as the sequence we're talking about here, but now we've extended it to all real numbers. And the only reason we do that is so that it makes it, we could use our old tricks, okay? And this told us, one of our old tricks is factoring. And so what I would do here is I would take the biggest exponent that I see, x cubed, and I'm going to factor that out of the top and the bottom, because that would cancel in that case. So the x cubed out of a 4 leaves 4 over x cubed. The x cubed out of an x leaves 1 over x squared. Or if you want, you can make that x over x cubed. On the bottom, we have x cubed over x cubed. And then we have 1 over x cubed. So simplifying just a little bit, 4 over x cubed plus 1 over x squared all over 1 plus 1 over x cubed. And again, this is a Calculus 1 problem, and in Calculus 1 we learned that we can split up limits amongst division, amongst fractions, and over sums, and so I'm getting way overly detailed here, but just as a refresher, we're able to split this limit across all of these different things separately. So the number 1 here. This is a step I would normally not write, of course. And then what is the limit of 4 over, we think of this as 4 over infinity. We're dividing 4 by really, really big numbers. We learned in Cal 1 that's, of course, zip, and so it's this. 1 is just 1 plus, this would also go to 0. All right, and that gives it for us. 0 over 1 is 0. So we were told to compute the limit of the sequence, but it's exactly the same as the limit of the function version. So that's going to give us 0. And if we want to check our work, we can actually plug in some numbers here and see if that makes sense. So again, the formula we were given is 4 plus n over n cubed plus 1. I don't have to do this, but I'm going to just to see if that really looks like it's vanishing to 0. And sure enough, if I plug in a 0, I get 4 over 1. That doesn't look like it's 0 yet, but maybe if I plug in another number, 1 gets me 5 over 2. That's already getting smaller. Plug in a 2, that gets me 6 over 8 plus 1 is 9. 3 gets me 7 over 27 plus 1 is 28. Oh man, 4 gets me 8 over 65, and sure enough, these fractions are going to, they look like they're going to limit to 0, but this is the proof of it by using our Calculus 1 techniques up here. Okay, so that's great. Let's do another example. All right. In this example, we're going to use L'Hopital's rule. L'Hopital's rule, of course, involves derivatives, and derivatives don't make sense for sequences. We have no concept of a derivative of a sequence, and we won't, because sequences are only defined for integers, and derivatives have to be defined for intervals of real numbers. So, but that's okay, because if I want to find that any sequence defined by this formula, and what I mean by that is that, well, I didn't tell you where the formula starts, but it doesn't matter, because all that matters is that it goes out to infinity eventually. And so any sequence, maybe starting with 0 or 1 or 7 or -3, as long as that we don't make this denominator 0, that would be a problem, that would converge to -1/5. And so anyway, what I'm going to just do is I'm going to take the limit as x goes to infinity, and I do have to rewrite it with this x so I can actually apply L'Hopital's rule, and then I'll get, instead of n squared, I'll write x squared plus 3 over 4 minus 5x squared. I don't have to use L'Hopital's rule for this, by the way. The factoring technique I just used a moment ago would always work. But as a reminder, the way L'Hopital's rule works is that if you have a limit of the form, and it looks like the top is limiting to infinity, the bottom is also limiting, well, it's limiting to -infinity. And that's not a real number, so I always immediately scratch it out. But before I scratched it out, I saw that I had infinity over infinity, and that's a L'Hopital form. All right, well, I'll just write it as LH form. Or indeterminate is another word for this infinity over infinity. We cannot determine by just plugging in what the value is. But that's okay. I can apply L'Hopital's rule, which a lot of folks write LH over it to the equal sign to remind us what rule we used, although we don't have to, so I'll just get rid of that. What it says is that if you have either 0 over 0 or infinity over infinity, you can take the derivative of the top and to take the derivative of the bottom. And it's important not to get this confused with the quotient rule. You don't have to do a quotient rule here. It's simply the derivative of the top over the derivative of the bottom, and that will have the same limit value if it exists. And let's see, on the top, I get the limit as x goes to infinity of let's see here, that's 2x plus 0 over negative 10x on the bottom, and I can cancel those x's to get negative. Once the limit, once all the variables have gone away, we can just drop off the limit. 2 over negative 10 is negative 1 over 5, and that is the value of the limit for this sequence I was given up here originally. And again, we can check that. If I just plug in numbers, let's start by plugging in 1. I get 4 over negative 1. Okay, plug in 2. I get, that looks like 7 over, plugging in a 2. I get 4 minus 20 is negative 16. Let's plug in a 3. We're going to get 9 plus 3 is 12. On the bottom, 3 squared is 9, so negative 45, that's negative 41. All right, and just by breaking out a calculator, we can figure out what that is. This is about, maybe I do need one more here. So I'll plug in a 4. I'll get 4 is 16 plus 3 is 19. On the bottom, I'll get 4 minus 80. So that'd be negative 76. Okay, let's figure out what this last number is here. 19 divided by 76. Oh, that's 0.25 right there. And this previous one right here, that was getting, negative 0.25. The previous one, 12 divided by 41, negative 41, was negative 0.29. This previous one here, 7 divided by 16, was negative 0.44-ish. These are approximations, and here's a negative 4. Anyway, the point being is that these numbers are getting closer and closer to negative 1/5. That's negative 0.2. And this fractional part past the 2 is going to vanish as we go out to infinity. So that confirms what we found up here using Hopital's rule. Let's take a look at one more. The squeeze theorem, something that we learned for real valued functions. This also works for sequences because it works for functions. So let's just go ahead and we'll use this directly with the sequence form. I want to know what the limit of sine of n over n is. Well, I know that sine of n over n, sine, that trig function, is trapped between negative 1 and positive 1. And the squeeze theorem for functions and therefore for sequences says that if you have an inequality of functions or sequences, then you can hit all sides of the inequality with a limit. And in the middle, we have exactly what we were asked to evaluate. The limit as sine n over n, the limit as n goes to infinity of 1 over n, and we know that the limit of 1 over x as x goes to infinity is 0. Same thing for the sequence, so negative 0 is 0. Limit as n goes to infinity of sine n over n, and this also goes to 0. And since our limit is trapped between 0 and 0, we conclude that the limit of sine n over n has to be exactly 0.